Hi guys, we have a probability question, a question that is at an intersection of probability and basic geometry. We'll try to solve this question together. Let's have a look at the question. If the lengths of the sides of a triangle are decided by the three throws of a single fair die, then the probability that the triangle is of maximum area given that it is an isosceles triangle is. Okay, so there are a few things that we need to keep in mind. The triangle has to be an isosceles triangle, right? Meaning two sides of the triangle have to be of same side length, right? Okay, second thing is that the side lengths are determined by throwing a single fair die, right? We know that a single fair die has six faces numbered from 1 to 6. So the length of the sides of these triangles have to come from 1, 2, 3, 4, 5, 6, right? Depending upon what those three throws are. Okay, so let's say that the three throws are represented by x, y, and z, and x, y, and z can take any value from 1 to 6 each, right? And that's how you will get the side of the triangle. So imagine if this is our required triangle and this is x, this is y, and this is z, right? Assuming that x and y are of same side lengths, meaning that x, y, z is a so x, y, z is the triangle. So this is a isosceles triangle. Okay. Now we need to find the probability that the triangle is of maximum area. So we have to maximize the area, right? So what all possibilities do we have? Now, before going forward, one common mistake that students make here is that, you know, while we do understand that isosceles triangle has to have two sides equal, what happens when all the three sides are equal, which is the case of an equilateral triangle? Equilateral triangle, guys, is a proper subset of isosceles triangle, and hence if you have all sides equal here, that will as well be part of our case. That will be a valid case, right? So we have to consider those cases also where all three values are same, x, y, z are same, right? Okay, now let's look at the possibilities of our x, y, z pair, triplet, such that let's say x and y equal 1. So these are the two equal sides. What are the possibility for z then, the third side? Can z be 1? Yes, of course. Can z be, so can we have 1, 1, 2? We cannot, because remember, if you know the basic triangle inequality, it says x plus y, two sides if summed up together will always be greater than the third side. So you take any two sides length, and if you add them up, you will have the length, combined length, greater than the third side's length. So obviously 1, 1, 2 cannot be a possibility because 1 plus 1 is equal to 2, right? It's not greater than 2. Okay, similarly, if you take the case where x and y are 2 and 2 apiece, then what are the possibilities for z? You can have z as 1, or you can have z as 2 as well. You can have z as 3 as well, because 2 plus 2 is greater than 3. And that's it. You cannot have z as 4. What if x and y are 3 each? You can have z as 1, or you could have 3, 3, comma 2, so on and so forth till 3, comma 3. What's the greatest value that z can have? Can we have a 6 over here as z? No, because 3 plus 3 is 6. 3 plus 3 is 6, so the maximum value we can have for z is 5, right? Cool. Now let's look at the values of x and y as 4 each. So 4, comma 4, comma 1, so on and so forth till 4, comma 4, comma. Now the maximum value of z can obviously be 6. It cannot be more than 6, right? Because the dice does not have a number more than 6. And 4 plus 4 is definitely greater than 6. So all possibilities of z from 1 to 6 are possible. Okay, what if x and y both are 5 each? you will have the same number of possibilities, right? So 5 comma 5 comma 1 up to 5 comma 5 comma 2. I am showing the intermediate cases through dots here, so it should be well understood. Okay, what about 6 comma 6 as the values for x and y? Again, you can have z as 1 through to 6 comma 6 comma 6. Oh, this should be 6. This should be 6. Cool. Now, these all are the cases, right? Now, if you look at the first case, this one, how many cases do we have? We have one case, right? If you look at this case, how many cases do we have? We have three cases, right? There is a basic mistake that students commit at this step. They really think that there are three cases here, which is not correct actually. Because, while it's true that this particular combination, wherein all side lengths are same, that of an equilateral triangle case, will have only one case, right? But the isosceles triangles, 2, 2, 1, now there are other arrangements possible also, right? So these 2, 2 and 1 sides can arrange amongst themselves also, right? So we have not considered those extra cases here, right? Same is the case here. So any isosceles triangle combination that we see in our entire list of triplets here, all of them will have more than one cases each. And all the equilateral triangle will have just one case, because there is only one way to select the sides, right? All of them have same side lengths, right? Okay, so what we will do is, first let's look at what all number of triplets do we have. So here we have three triplets, here we have 1 through 5 triplets, here we have 1 through 6 triplets, 6 again and 6 again. So in all we have 18 plus 5 23 plus 4 27. So in all we have 27 triplets here, but these are all not our exhaustive cases, right? So out of these 27 triplets that we are seeing, obviously there are 6 cases of equilateral triangle in one each, right? Now we know that for equilateral triangles there is only one case. So if I bifurcate 27 into 21 and 6, so 6, for 6 equilateral triangles we have 6 cases only, right? Because there is one case corresponding to one triplet of equilateral triangle, right? There is no other way to arrange 2, 2, 2 or 3, 3, 3, right? Just one. Okay, for the remaining 21 cases, which are that of isosceles triangles, in how many ways can each case be arranged? So if you have something like 2, 2, 2, 2, 2, 1, right? So the number of ways of arranging this triplet, right? How many arrangements are possible? So 3 factorial divided by 2 factorial. Why? Because there are two identical items. So in a sense, there are 3 cases, 3 possibilities of arrangement for every isosceles triangle that we have. And how many such isosceles triangles do we have? 21, right? So the number of arrangements for these 21 isosceles triangles is 21 into 3, which is 63, right? Which is 63. Now, in total, we have, so these are 63 cases. So in total, we have 69 cases. So we have 69 isosceles triangles to consider from. This is our exhaustive list. So, we are required to find the probability that the triangle's area is maximized. So total number of cases, total number of equally probable cases is 69 that comes in the denominator. Now we need to put the total number of equally probable favorable cases. So favorable cases where the area is maximized. Now remember, when is the area of an isosceles triangle maximized? When it is an equilateral triangle. when there is symmetry, right? So in case of equilateral triangle, the area of any isosceles triangle is maximized. And given the dimensions here, the biggest dimension is 666, right? So this is that triplet which will ensure maximization of triangle area. And of course, it's just one out of those 69 cases. So what we have in the numerator is 1. So 1 by 69 is our correct probability. Choice E is the correct answer. Thank you.